What specific problem does the LightThinker method aim to solve in the context of large language models, and why is it essential to address this issue?
The LightThinker method aims to solve the problem of excessive memory overhead and computational costs associated with token generation in large language models, LLMs, during complex reasoning tasks. As LLMs transition from fast to slow thinking modes, they generate a large number of tokens, which leads to a significant increase in memory usage, particularly with the KV cache, and a quadratic rise in computational costs due to the attention mechanism. Addressing this issue is essential because it severely limits the practical efficiency of LLMs in long text generation and complex reasoning tasks. LightThinker dynamically compresses intermediate thoughts into compact representations, significantly reducing the number of tokens stored, and thus lowering both memory overhead and inference time while maintaining comparable accuracy. This approach not only enhances the efficiency of LLMs, but also provides insights for future inference acceleration strategies.
How does the proposed LightThinker method work? Please illustrate the methodology step by step, including how token compression is performed and the role of special tokens in this process.
The proposed LightThinker method works by dynamically compressing the reasoning process of large language models, LLMs, during generation. First, the original dataset is reconstructed by segmenting the output into subsequences, either at the token level or thought level, and inserting special tokens that trigger compression. When a thought is generated, the model compresses it into a compact representation using hidden state compression, where the hidden states of the lengthy thought are reduced to a few special tokens known as GIST tokens. These GIST tokens store the essential information needed for subsequent reasoning, while allowing the original lengthy thought to be discarded. During inference, the model utilizes a thought-based attention mask that enables it to attend to the question, previous compressed content, and the current thought, facilitating effective reasoning based on the compressed information. This process significantly reduces the number of tokens stored in the context window, thereby lowering memory overhead and computational costs.
Can you provide a simple example that demonstrates the inner workings of the LightThinker algorithm, detailing the compression of thought chains and how reasoning continues from the compressed content?
The LightThinker algorithm operates by dynamically compressing thought chains during reasoning to enhance efficiency. For instance, when the model generates a lengthy thought step, such as, to solve the equation, first isolate the variable by subtracting 5 from both sides, it compresses this into a compact representation, like CT, which retains the essential reasoning without the full detail. After this compression, the model discards the original lengthy thought and continues reasoning based solely on the compressed content, allowing it to focus on key steps rather than the entire thought process. This method significantly reduces the number of tokens stored in the context window, thereby lowering memory overhead and computational costs. The model learns when to compress and how to generate subsequent thoughts based on these compressed representations, effectively streamlining the reasoning process.
What are the theoretical and practical benefits of using the LightThinker approach compared to existing methods such as an LLM, H2O, and vanilla?
The LightThinker approach offers significant theoretical and practical benefits over existing methods like an LLM, H2O, and vanilla. Theoretically, LightThinker decouples the tasks of compression and generation, allowing for enhanced contextual understanding during compression, which is not possible in an LLM where both tasks are tightly coupled. Practically, LightThinker achieves a 70% reduction in peak token usage and a 26% decrease in inference time compared to the vanilla model, while maintaining comparable accuracy with only a 1% drop. In contrast, H2O increases inference time by an average of 51% on Qwen, despite reducing memory usage, indicating that LightThinker balances efficiency and performance more effectively. Additionally, the thought-level segmentation function used in LightThinker outperforms token-level segmentation, leading to improved accuracy and better semantic preservation during compression.
How was LightThinker validated or tested across different datasets, and what metrics were used to assess its performance? Can you explain why those metrics were chosen?
LightThinker was validated through extensive experiments across 4 datasets: GSM-8K, MMLU, GPQA, and BBH. The performance was assessed using several metrics: accuracy, ACC, to evaluate effectiveness, inference time, to measure efficiency, peak number of tokens in the context during inference, peak, and the dependency, dep, metric to quantify the amount of historical information each generated token relies on. These metrics were chosen to provide a comprehensive evaluation of both the effectiveness and efficiency of LightThinker, with accuracy reflecting the model's reasoning capability, and the other metrics addressing the computational efficiency and memory usage during inference. The results indicated that LightThinker achieved a good balance between maintaining accuracy and significantly reducing inference time and memory overhead, demonstrating its effectiveness in practical applications.
What limitations or potential drawbacks did you identify with the LightThinker method, especially in terms of the compression process and reasoning accuracy?
The LightThinker method, while effective in reducing memory overhead and inference time, has notable limitations, particularly concerning the compression process and reasoning accuracy. One significant drawback is that the compression is not lossless. It selectively retains only predictive information crucial for future reasoning, which can lead to information loss during the compression steps. This was evidenced in a case study from the GSM-8K dataset, where the model arrived at the correct answer during the reasoning process, but made an error in the final output due to insufficient sensitivity to numerical values during compression. Additionally, the method sacrifices some accuracy, specifically a 1% drop in accuracy for the Quen model and a 6% drop for the Llama model, indicating a trade-off between efficiency and precision. These issues highlight the need for further refinement in the compression strategy to enhance reasoning accuracy without compromising efficiency.